Greetings and welcome to the second installment, Pioneers of Sonic Excellence. I'm your host, David Hyman. On this podcast, I've got no other than Michael Borresen, absolute genius brain working across industrial design, material science, electrical engineering, mechanical engineering. He is a modern day audio renaissance man who has this unique combination of skills across all of those disciplines. And he is pushing the boundaries in audio in his company, Borison Acoustics, making some of the best speakers in the world. AVIC Electronics, making some of the best amplifiers, preamplifiers, and DACs. And Ansuz cables. He's truly doing it all. And when you go into one of his rooms at an audio show, it's like walking into a different planet. You go from room to room in an audio show, everything sounds kind of the same. And then you walk into one of his rooms, and all of a sudden, everything sounds scary real. I'm so honored to have him today. We go pretty deep in a lot of different subjects, so please enjoy.
And if you wanted to see me, I entered into this business about 20 years ago, and it has been a passion for me to work with speakers, mainly speakers, for ever since I was a kid. My father. There was a fire in the ScanSpeak factory, and my father was buying the excess drivers from the insurance company afterwards. And he had a wood shop. He could build cabinets. So him and a friend made a small speaker production, and I was maybe 10, something like that. And that meant that I had a cabinet of ScanSpeak drivers when I was a kid. So every week a new project. Pretty soon I got old enough to run the machine, so I could bush up some wood and make some boxes and try to figure out how crossovers was working. And I think that was where I got my initial feel and enjoyment of creation into this audio industry. Also pushing that a lot was I had a father that said, can you do it better? So I was always, I wanted something. Can you build it yourself? Can you do it better? That was always the mantra of my childhood.
So when your father started this, did he turn it into a product and sell it, or did he just make a few?
Yeah, he did. He did, because wow. I think a limited quantity. I think that maybe 500 drivers, 500 tweeters, and that's 250 pairs of speakers. I think they built that over a few years. And
was there a brand? Was there a brand name? Okay.
No. There was no brand name. But it was veneered boxes cut together in the corners with a grill and front off, looking like any other wooden square box speaker at the time. And I think they were actually.
What year do you think this was?
It was maybe late 70s. Yeah, I think it was actually maybe mid 70s. Yeah, mid 70s.
What do you think it is about Denmark and this cultural connection to loudspeakers and speaker building, amplifiers and electronics as well?
I think the main connection actually came out of a very few people. It was sort of like, you have a company. One of the first ones came up was ScanSpeak, and ScanSpeak consisted of a few people. Ragnar Lian, one of them, and Eivind Skåning, another one of them. And they started building drivers. And then they got, I don't know if they needed to take investors in or whatever, or maybe they disagreed on something. But out of that came new companies. like Aavik Skåning founded Dynaudio, and Ragnar Lian went to make SEAS. So all of these are interlinked, and when people that sort of like get elevated to some significant role in a company get to know the inner workings and the know-how of how to do, then all of a sudden this company is maybe downsizing and leave it a guy on the side with knowledge, creating, peerless, creating,
Dolly,
VFAC, creating.
Dolly
So
also.
all of a sudden you have a luster of maybe 5-6 guys and 5-6 small companies, some making finished speakers, some making drivers, some making, and all of a sudden you have a group of companies, all of them at a fairly high level, because there was a few guys who really pushed the performance up, like Ragnar Lie and Aavik Skåning doing the SD system with the copper caps inside the drivers and stuff. That really elevated the possible performance you could get out of a speaker driver. And I think that created a foundation for these companies.
Interesting. And so after this early exposure through your dad, where did it just continue as a hobby for a long time? Did you immediately?
Yeah, I think that making speakers was always a hobby for me. I took a mechanical degree at university where my major was mechanics and materials. And during that tenure, I ran into my neighbor where I was when I was studying, and he was a freak like me. We built big apogee type of speakers. I made a subwoofer as big as a house almost. And these projects just kept on during the studies, during university. And then later when I got a job, it continued to be a hobby. And I was not very far in my working career when I founded the Rideau speaker company in 2001, something like that. And from then on, I've been more or less full-time in the business. At the university, I was out and in again at the university. It was not a straightforward process for me to get a degree. So I came in into the university off semester. So I had to spend some time doing something else. And that tenure put me through analog electronics. So I've had both, the analog electronic parts and then the mechanical part. And a speaker sits right in the middle of that.
Did you have jobs as an engineer before Rideau?
Yes, I had 2 jobs before full time in the audio industry. One job was designing and doing the R&D work on airport trolleys. So if you go to Schiphol Airport, you see the trolleys there. You can run around and think about me. And if you go to Copenhagen Airport, you can run around with the shopping carts in there and think about me. So that was my first job. And while I was there, I actually got hunted into a company doing satellite communication. So I shifted there, and I had a job there for 5 years, I think, where I was head of the mechanical department and also doing, we had something called PIC, which was Product Introduction Center, where we did PCB layout. We did a lot of the radio frequency PCB work and the radio frequency design on antenna tuners. This company was not only satellite, it was also radio communication. It was called Eurocom Industries. And there I learned a lot about high frequency noise and how to combat that. And that is some of the things I've taken along with me where I am now.
So when you first started Rideau, like what was it? Explain to me what you were feeling, why you started, what that leap of courage looked like, and
I continued this hobby, with my old friend. We made these very big apogee-like speakers, big as a door. And I really like the way that treble worked, that ribbon tweeter work. And I was considering how to make something that was more an industrial product of a ribbon tweeter. So late 90s, I set out to do a design around that and develop a tweeter there. And then I tried to sell it to ScanSpeak and have them marketing it out in the market. But one of the guys down there didn't like it because it was not loud enough. It has good enough sensitivity, but it was too mild. There was too little and too much this kind of treble. So it's very soft. And when you have drivers that has a normal breakup and has resonance, then a tweeter like that, you cannot hear it because it's drowning in all the other shit stuff the mid-range drivers did. So they did not feel that it fitted their program. But I thought that the tweeter was really, really good. So I have this old friend who's also my business partner today, Lars. And so I met him while doing airport trolleys. And I said, I have this tweeter. We need to make speakers. And he was just looking at me and shaking his head and said, no, the world does not need any more tweeters or any more speakers for that matter. There's enough. So I built some prototype speakers together with drivers from Audio Technology, the son of Eivind Skåning, one of the oldest pioneers, has a company today called Audio Technology, making wonderful drivers used in Rockport, used in many speakers today. So his drivers and my tweeter created the foundation for Rideau.
And Lars was at Nordost. Did you know him?
Lars was at Nordost at that time. Yes, he was. So my idea was get Lars interested. He could sell the thing and I could design it and get it produced. And then we had a company. And of course, things are not that easy. But essentially that was what we did. And we ran that company together and grew and made good speakers. And then in the financial crisis, when that hit, we lost the control of the company. So Lars and I were just no longer main shareholders. We were under the direction, company direction and company leadership from John Jensen and Dantax. And we stayed around that and grew the company Rideau with new speakers, better speakers, larger speakers for about 5 years or something like that. And then it was in the cards that we needed different direction. We needed different directions. I think that yeah. So we parted ways, and Lars and I quit. Lars quit Nordost. I had a little fling with designing some of the Nordost things, and I quit or got dumped or whatever. And after 2 years there, then we started the Ansuz company with the cables. Essentially, got into competition with Nordo. That was now 10 years, 12 years ago, maybe something like that. Yeah. And what I learned by doing these antenna tuners, this radio communication, how to suppress noise, all of that was put to work in the Ansuz company in the cables. I learned that cables are only as good as their bad antennas. If you have a cable fixed length, it's a very good antenna. And the job is to create a cable that is very good connection, but very poor antenna. So it doesn't pick up all the radio frequency noise we have hanging everywhere around us. And this Nikola Tesla thing, the Tesla coils that we use are actually inverted Tesla coils, where the Tesla coil is a huge amplifier. Then if you reverse that process, you can have something that's a huge cancellation. So if you manage to make something where the speed, the propagation speed and the length fits high frequency, then, and you cancel it, you make a coil, and inside of that there's another coil but wound the other way. If you do that, then you can get into a situation where most, or a fraction at least, of the high frequency noise is cancelled, so that your antenna you have in your cable is not picking up radio frequency and injecting that into your system, but instead maybe counteract some of the radio frequency we have out there. And that is a major part of making good cables. And that's a major reason why I believe that our Ansuz cable are at a level where nobody has been looking, because nobody's looking at these things. I think most cable manufacturers, for them, what I'm saying is voodoo. It's a no nonsense. It's out there where people, but it's a very scientific thing. And I learned this in a company whose very existence was depending on making better transceivers, radio transceivers than anybody else. You know, global marine distress and safety. If you can listen a little deeper into the noise floor, maybe you can save some people. If you can listen a little deeper into what other people are talking about, maybe you can find better fishing grounds. So that is a very big competitive edge they had in that maritime communication. And that's where I learned my things.
I love that you pulled fishing in as an avid fisher. I can see you out with your reel thinking about how this applies to yeah. So to that, like with noise cancellation, you know, this is an active cancellation. It's inside. It's not.
Yeah, it's active in that respect. The thing is that you can have a passive version of this, but you can also making it active. And what you do is that you make something active that is a zero. So you sense what goes on in the coil and try to make that a zero. And if you can feed a signal from the coil into an amplifier that reverses the signal and puts it back in the coil, then you have an active noise cancellation. A little bit the same as you do with the microphone, pick up airplane noise and feed it back into the speakers. So essentially you're killing the ambient noise from the plane. That's how that is done. And I think,
or these like ultra symmetrical balanced connections that are doing some form of cancellation.
Just reversing the phase on something you pick up on and feeding it into itself. Of course, there's a little delay, and that sort of limits how high frequency you can actually do this with. But it's doable.
Yeah, something that I've become aware of recently that I was skeptical is getting exposed to streaming servers high frequency noise, and how their high frequency noise actually has a profound effect. What we hear,
it's unbelievable how effective a good LAN cable is. It's unimaginable, unfathomable how good music streaming becomes when you have a good switch. I mean, if you have a switch, the problem with the internet, as you are of course very much aware of, it's a floating thing. There's no ground there. There's nothing. There's no way you can actually get noise out of it. But if you can make an artificial ground inside your switch, you have a channel to lead the noise that is the World Wide Web of noise, I tend to call it. But a good switch like the ones we have in Ansuz and a good LAN cable, it's unbelievable how much it cleans up what you can get from streaming. And streaming has surpassed CDs a few years back and never looking back. And I think that every time these music services, Cubus and Tidal, whatever, improves their formats more and more FLAC, you just get closer and closer and closer to the real deal. And we should be very happy that music was digitized. Philips and Sony came out with the CDs basically what they did was they killed off the joy of music because they sounded so bad. But I don't think the process of getting something from analog into digital was flawed in the same way. Because if you think about it, analog to digital is sort of like monitoring and taking levels. I take a sample now, I do that 44,000 times a second, and you get a catalog of values, 16-bit values, and you stock them. But there's no intrusion in that. It's an observation.
I've asked myself this question a lot. All the great improvements we're making on the playback, how important are they in the code side? And are we all screwed?
I think that
interesting.
The original idea of the PCM is that you have a value. You have 16-bit, which is 65,000 values, and you take them as points. And then the playback has always been in points. So you have ladder DACs. And people still swear to ladder DACs, but ladder DACs are flawed because they introduce noise. Maybe they introduce noise every time you switch 44,000 times a second, or even if you double it, it's just doubling up on the noise, essentially. And that's high-frequency noise you need to get rid of. Some of it you can get rid of because you put it through a low-pass filter, but that's just the low-frequency artifacts of the switching. The high-frequency is very important. It's impossible to filter out because two PCB traces next to each other, and then you have a small capacitor, and the noise just bleeds into your system. And we know for a fact that when you have this switching noise, it just kills. It makes the digital music pointy. It's not playing from below like a turntable or playing below like a tape is. So when you have a ladder DAC type with this switching, you have this pointy thing. And you can do it, of course, you can do it a little bit better, but that doesn't really, that process is flawed. It's simply flawed. Something's wrong with that. And that is very hard to get back to something that is not flawed.
A friend of mine who's an audiophile living in the south of France said he observed waves coming to the shore, and when it rains, somehow the waves completely dissipate. And it has something, he's drawing an analogy to how high frequency energy above the audible spectrum can actually kill or change the waveform of what we actually perceive and hear. So what are your thoughts on why this high frequency noise has an effect in the audible spectrum?
This is where I think that the theory sort of meets a boundary, because it's very audible. When you clean out noise, when you don't have it, you hear you don't have it. When you have it, you don't. It's just sort of like the limitation of the system, and then you take noise away, and the system gets much better. So I'm struggling to find a theory for why this noise is as bad as it is. What we have done in our latest version of the DAC in the Aavik is that we have created something that is what we have done actually is you take the 16-bit and then we upsample it to DSD 512. So we have a DSD signal, and in that the analog is embedded. So instead of having something that is a switch process, point for point for point, then we have the analog signal in there. So it's just a matter of integration or low pass filtering to get the music signal out. So we move instead of a discrete process into a continuum. And then we get this warmth and play from below and energy and not pointing at you. So there is a remedy to get the analog out of the digital.
I know some other companies like Nagra and Playback Designs are converting to DST and DST.
Yeah, but there's a big difference between the DST because that's essentially a 1-bit signal, just upsampled a lot. So DSD 512 is like 22 megahertz. Here, instead of having 1 bit, we have 16 bit, and so essentially we have 65,000 times the theoretical resolution. But you don't need that. I mean, but then you don't have to translate PCM into something different. You don't have to translate it PCM to DSD and because you are, of course, with all the friends you have, aware that DSD mixing desks is a rare breed. So everything is PCM at one point. So for me, it's always better to keep it in PCM. So my task was, how do we create a conversion that is a continuum rather than to have to make it DSD and then go from there? But the DSD conversion process is much better than a ladder DAC. But it's even better if you take the PCM signal and treat it as DSD and upsample it to 22 megahertz and then low-pass filtering just to get the music signal out of it. Then you can really do audiophile things with discrete op amps, with really, really good audiophile components, stuff like that. Because you take the flawed process out, the process that creates the problem, you take it out and replace that.
Interesting stuff. Going back to Borresen, the loud.
Yes, let's go back to the speakers again.
Yeah, I mean, it's impressive to me that there's been a philosophy in your speakers that seems to carry from the very beginning, which is this very kind of narrow front baffle, smaller drivers, more drivers, and that has kind of carried from your earliest designs until now. So, what is it about specific type of design that that resonates with you or you find to be?
Yeah, I think that if you take a laser and put to a bass driver, if you take something bigger than 8-inch, no matter how stiff you want to make the cone, it just flexes. And the radiating area in a transient is not more than 4.5, 5-inch anyway. So why make drivers bigger than that? You just make a driver that creates a situation where it will create its own noise because the membranes are flexing. So I think that's the reason why this philosophy is carrying and still being developed.
Mm-hmm. So many different speaker manufacturers kind of go down a different path. Some take obsession over the inertia of the inertness of the cabinet, and they're messing around with carbon fiber and aluminum. Some companies say no cabinet at all. Let's remove the distortion that way. You seem to put most of your energy and focus efforts.
It's pretty clear that making cabinets is sort of like a quest for optimizing a given, but creating new drivers is making a new paradigm. So if you can really look at where the issues are in a certain concept and address that and do active things to iron out the problems in a design, like a speaker driver. It was created 100 years ago by Peter Jensen. I think he was from California, or he was actually a Dane but living in California. But he invented, and nothing has happened since. It's still a magnet and some iron and a voice coil, and that structure has not changed. It has, for everybody in the business, been a given. This is how you do. Sure, you get a neodymium magnet, you can compromise, you can change things, you can put in copper caps, but nothing radical. And I had a quest to see how to make speakers more efficient. And the best way seemed to put more iron into the driver. But the problem was that every time I put more iron into my magnet system, I got a driver that sounded maybe louder, but worse. So there was sort of like this intricate thinking about what does iron do of good? Does it do anything good? Apart from carrying the flux. But then you realize that the voice coil is an electromagnet. So the iron will also carry the flux of the electromagnet. And where Scanspeak and Dynaudio, the Skånings, Eivind Skånings and Ragnar Lian were brilliant when they invented the copper cap. I'm not sure they entirely understood the working principle of that. But they saw that the inductance curve got flatter. But what happens is that the copper cap counteracts the moving magnet system you get in the voice coil, the electromagnet. It sort of breaks that. It tries to DC lock. So I thought that if we could get rid of all that iron, that actually promotes fluctuations during playback, if we could eliminate the iron altogether, then we will be in a much stronger situation than instead of putting a small, thin, 1/10 of a millimeter thick copper cap in the magnet system. Then we could do a ring of copper or a ring of silver or whatever.
And
so
and
once
the
I got
iron
the idea,
saturates at some point where it starts having diminishing return.
Yeah, the thing is with the iron that it's very easy to relax it, make it less flux, but it's very hard to, when it's near saturation, to increase the flux. And that variation up and down, that hysteresis loop is not very linear. That means that you put in distortion in your music signal from the playback itself. So it's sort of like if you have a transient, it distorts more than in a soft sine. So you don't really see the dynamic aspects of iron, but it compresses the music signal. And where we see it the most is that the soundstage sort of gets flat. The more iron you have, the flatter the soundstage gets. You don't get this big. But then when we started the Borison speakers, after we left Rideau, I said to Lars, we don't do anything on speakers unless we have something really, really, really special. And that was when I got the idea to make this motor system without any iron to conduct the flux. So we have a patent on an iron-free motor system. Iron-free, I do like this because there is iron in the neodymium magnets, but it's essentially 4 neodymium magnets, 2 in the pole piece and 2 outside, where you squeeze North Pole to North Pole and South Pole to South Pole, and that ramps up the flux so it gets usable for driving a speaker. And in between these 2 layers of magnets, we have silver rings or copper rings. Copper was where we started, silver was where we ended. Silver conducts maybe 6 to 8% better. So that creates an even stronger lock on the DC flux and lowers the induction. And we're talking about a lot. We're talking about this magnet system eliminates 90% of the induction of the driver. So it's not a trivial thing. It's a really, really big thing. And that creates a driver where the rise time is unparalleled. And that opts for a resolution that no other speaker manufacturer can get.
I mean, whenever I walk into your rooms at a show, it just sounds so much different and so much clearer than what I hear.
Yeah, but you should spend some time with one of our, even our cheaper setups. You should spend some time with that, and you will have a totally different view of how Dean Martin sounds, how Mr. Blue Eyes sounds. I think that we have seen this treasure trove of artists that are there for us and for our kids and grandkids and whatever, because Sony and Philips digitized everything in the 80s. We should be happy about that.
Your flagship mini is probably the most expensive speaker per pound ever made.
I don't know. There are many speakers that are more expensive than that one. But sure, yeah, they are.
No, I mean, $100,000.
The thing is,
you've really broken through, but it also sounds better than anything at that size I've ever heard or comes close.
The thing is, David, if you take no compromises, I mean, the baskets in there are made from 3D printed zirconium, and that is just the magnets in itself, because zirconium is used in nuclear power plants and forms the shell layer around the fuel pellets. So when you start working with zirconium, the IIA comes knocking on the door and says, "Hey guys, what are you doing?" "Oh, we're making speakers." "Yeah, right, you're making speakers. Why do you need this?" "Yeah, come take a look. This is what we do." But but what many people don't realize is that the basket is a spring that's placed between the force and the membrane. So when the membrane is moving out, the magnet is moving back, and you put this springy material into that. So that the tonality of that material is extremely important. And once you hear the difference between that and a die-cast magnesium or a die-cast aluminium, you would just shake your head and say, "This is not possible. This is not possible." But we have this guy in our company, Lars, running around testing out every fucking material he can get his hands on, and then he goes to the technical university and asks to the guys who do surface treating for the ITER system or the big particle accelerators in CERN and stuff like that, "What kind of exotic materials have you got?" "We have this material, that material." And then we do a coating on maybe a titanium piece or a piece we know how it sounds and see if it's better. And every week there's a new experiment. This guy never gets old doing this. He loves it, And then he tests and then he calls me and says, "You should have a listen to this. This is bloody fantastic." And it is. I mean, it seems like every time there's a material that our body accepts, like zirconium is a material our body accepts. They use it for surface coating on the titanium screws that you screw into your jaw. They use zirconium for covering wires on your pacemakers. So it is a material our body likes. Like titanium, it's a material our body likes. I think you have screws in some places you have screws. Titanium.
I studied this a lot because we've got a guy out here who started shutting up the little wooden discs, and he was obsessed with the fact that Mapingo wood related to ebony resonates in a way that humans like. Some things we hate, some things we love, like bronze bell. We also love carbon because our bodies and our bones are made of carbon.
You can ask yourself what we like. There are some very, very good guitar builders who swear to putting titanium threads on the guitars because they sound better. Yeah. You don't ever see any aluminium put in music instruments, do you? It's a shitty material. It sounds shit. It resonates bad. We don't like the tone of that. So there's something we like and something we don't like. And of course, making something exotic and high-end is a maneuver into that territory as well. And that's where you just have to trust your ear and trust your instincts and trust your feelings. And that is a story that is harder told than when you have something objective like noise cancelling in a cable, when you have something objective like taking 90% of induction out of a driver. You have something objective like making a Class A amplifier that is Class A all the time, never goes out of Class A. That is objective as well. So these things are easier to argue. But that doesn't exclude the materials as being a very, very big part of what we have. I mean, there's a good reason why a Durand turntable, a tone arm, has a wand made from exotic wood. There's a good reason why the old Pluto turntable with the citrus wood platter was sounding fantastic. So these things tend to make themselves famous. And then when you look at it afterwards, you realize, oh, maybe this was the reason why it was so good.
The driver membranes themselves, I mean, you were probably probably one of the first to really pioneer diamond impregnation on a driver that wasn't a tweeter. You know, where's your thinking gone since then, and kind of where's your head now?
The thinking has gone in that it needs to be very stiff and very non-resonant and very light. So I think that from where we were in 2003, I think I made the first ceramic membranes with diamond on top, to now is a journey into composite, carbon. It's a journey into having uneven stiffness but homogeneous weight, so we can take away the resonances, because every membrane has a resonance. If you can move the resonance up and out of the usable area, there's still a resonance, but it has less effect and you can filter it out. But if you can remove the first order resonance altogether by making the environment where the resonance stands impossible to have a resonance. And this is where my understanding from working with materials in university and the ability to simulate composites, my ability to know and maneuver in this world of materials is good. I know what I want, and now I also know how to get it. So the membranes we have pioneered on the M, which is a sandwich from 4 millimeter honeycomb with a layer of carbon on each side. But the carbon is not any carbon; it's a spread toe carbon. This is why you have these. You see them on some drivers in thin plies, but thin plies is for me too soft. You get you get too much energy sucked out of the music. I want something stiff, but I want to create an environment where you don't have this first order resonance in your system. So these checkers that you see in our X speakers are 2 layers of spread toe on a 4 honeycomb in between, and that is a revolution in terms of what a speaker membrane can do. It's very light, it's very strong, it's very, very high frequency first resonances, and it's very small resonances, starting 12, 15 kilohertz something. And we use it to 2.5. So basically the noise is way out there. And once you get that, you get something that really is good to our tweeter, because then you have the same clarity in the upper mid range as you have in the lower tweeter. So you don't have this disjoint.
Going back to my earlier question, like, do you feel, how does Borison handle cabinet resonance? Is it through the porting, or, you know, what's your philosophy on cabinet resonance, and how does Borison?
I think that the cabinets needs to be at the right size to fit the driver acoustically, and then they can't make a bad sound. I don't mind a cabinet vibrating if what it vibrates is good. I don't like closed cabinets, because all the energy you put in needs to come out. If it doesn't come out through the cabinet, it comes out through your membrane. It comes out through force on the backside of the driver. It has to come out. You cannot have something that just takes energy and doesn't do anything with it. It's like a magnetic monopole. It doesn't exist. So for me, closed cabinet designs has always been like this. You know, they always have this hollow sound to them. And I think most of it is because of pressure building up behind the driver that needs to come out, uneven pressure. And there I find that ventilated cabinets are by far the best.
So much of this is about benevolent resonance. So it's
I want, when designing drivers, I want drivers that can power handle without a cabinet. So I mean, I can use the cabinet not to power handle, not to put a spring behind the driver. I don't need that for my driver to power. I want a driver that can power handle by itself. That means I can use the backside however I please. And now we make 2.5-way speakers. And if you look at how I port the mid-range, it's not ported, it's just ventilated. It's just air breathing out the back. Also on the tweeter, air. So essentially, it's a damp dipole in a way in the mid-range. And then behind the bass, I can make a resonance. I can make a port with a ported resonance because it hasn't any gotten. We rolled it off 120 hertz, so there's no mid-range there. So it's just bass. And that means that I can make a very good low frequency extension from that. So I have more freedoms in my ability to create speakers that most companies do, because I know the drivers, I know how to design the drivers, I know how to manufacture the drivers. So I have a huge advantage rather than going to Morel and say, can you do this for me? Can you do that for me? And every company that sells drivers, they look at return rate. They look at, and they are not in charge of making high quality. They are in charge of making what the customer wants. So you have something where the interest of the speaker manufacturer is, I need to make sure that I don't get any drivers back. So I need to be on the safe side, where I can go much closer to the limits on everything.
And as a driver designer manufacturer, I would imagine it gives you more freedom to build simpler crossovers.
It makes me, I have 100% more freedom than anybody else in this business. I mean, I can go for titanium voice cords. Most companies are reluctant to do that because they build up heat. For me, heat is not a problem because I have a copper or a silver pole piece that will suck the heat out. So I have a very good heat sink built into the driver that is not the voice cord. So there's many places where I can do things a lot different than other companies because we have this iron-free magnet system. I have built voice coils where I put a winding on the inside of the titanium and a winding on the outside of the titanium. Then I run these in parallel, and that lowers inductions by 50%. But it's not every company that can manufacture a voice coil like that, because you have a mandrel to wind inside, you put and then you, I mean, it's complicated.
Well, let me ask you a question.
But it yields good results.
Where do you think these ideas come to you from? Like, I mean, it's a form of creativity.
I think it is a form of creativity, but in everything, you need to have a problem to solve. I mean, once it's clear for you that this is not the way to go, we need to avoid this. And then you can ask yourself how to avoid that. And then you go to sleep, and then you wake up, and then you have another idea, and then you try to sort it out. I often say that if you have a company, it's a little bit like buying a boat. I mean, you can go on a boat. It's a key. You go out and walk the deck and see the cabins, and everything is nice. But the clever guy says, "Can you pull it ashore? I want to see the bottom of it. I want to understand what's in it. How does the keel look? What is this?" And once you have that curiosity, that nature of curiosity, I mean, how the fuck did you make Grace Note? You can ask yourself the same question. You excel and optimize your things, your process, your ideas where you are. And now this is a passion for me. So I look into this and I dig deep. I go where conventions.
Is there anything you do lifestyle wise to encourage your innovative thinking?
I have a good coffee machine.
Okay. So coffee is one of your secrets.
Yeah. So I think I have been very fortunate. I've had the privilege of being able to live of my passion always.
Do ideas often come to you like when you're sitting in a shower, when you're fishing? Is there a time where you can look back at some of your idea, any parallels?
I think the revelation. I think it's a slow development process, but I think the revelation of creating the iron-free magnet system or creating the DAC is a process where we started actually doing. I did a DSD DAC that was sort of like a filter a DAC-less DAC with a DSD. I saw this analog, and then I have a very good friend and colleague in the company, Mikkel, who do a lot of the digital work for us. And I talked to Mikkel, can we do the same with the PCM as we did with that DSD? Can we do the same? Can we do the same? And then all of a sudden he came and said, I think I found a way, because there's coming a new chipset that doesn't have the limit of upsampling that we used to. I can upsample that to 22 megahertz now. And let's do that. And then we ended up with a shitload of noise, and then we needed to find a way to get that noise out of the system afterwards. And we found that by adding 32 samples together, we got rid of the edges of the noise, because essentially when you have a square, and then all of a sudden it changes. Then you introduce a lot of noise. But by taking 32 samples at 22 megahertz, all of a sudden one of these samples starts looking up. Then you get a floating or gradual change to the next level. And by doing that, we got rid of the noise and we got the system working. So there was a sort of like processes in the process. First, you get the idea and put out the question, can we do? And then you get minds working at that. And all of a sudden you find the solutions. And when you find the solution, they're pretty simple, basically. So everything good is simple.
Going to your amplifiers, I mean, you're one of the earlier kind of people to push maybe a Class A coupled to a switch mode power supply, right? There was Class D, and you kind of innovated off of Class D, maintaining the switch mode power supply.
The thing is, I worked together with a guy that ended up in Ice Power. And we talked a lot about what is a limitation, what is a problem, what is us. And then a company, Pascal, came along and they solved a lot of the issues around Class D. And you have to realize Class D, you get a new chipset every year, because what is good for Class D is also good for power electronics. And the Teslas need to drive, and the windmills need to invert current into the grid, and all these things. Taking transformers, they are basic. Inverters are taking transformers out. You don't have a transformer station. Well, maybe in the States you do still, but now everything is inverter based in Denmark or in Europe, and the power is getting from all kinds of sources in sync and everything. Inverters are doing that, and the problem with transformers is that they are big, contain a lot of iron, contain a lot of windings that are like this in together. And through these windings, you have a lot of parasitic capacitance. And that means that a transformer has high inductance. It's slow to give power. And it has a lot of all the noise from the grid bleeds right through it. You cannot filter it out because there's capacitance that simply leads the noise. And you can only suck power 50 times or 60 times a second when the voltage is high enough to open up the diodes. So you have a switch there 60 times a second, pushing the amplifier off balance. When you have a resonant mode power supply, you have something where the noise is in microvolts, and you can suck power 400,000 times a second. I mean, you can also take. It's very nice to drive a car with a combustion engine, but take a Tesla plate and feel the acceleration. It's a little bit the same.
It's so interesting to me because we have like OTL amplifiers that kind of saw that transformers were a problem. There were kind of early tube guys like David Burning that was doing like switch mode power supplies. You know, you have such strong philosophies on both sides. Some think that the noise of the switch mode power supply.
Yeah, but I think that if you take sort of like the Meanwell solution that others use, those are squares. those have the same switching issues as we talk about the DAC. You have switching on every time. But if you take a resonant power supply, they run on sines. So everything is soft. So there is no switching issues. There's no switching noise on a resonant power supply. Instead, there's a density, and you can suck power a lot. You can fill up your capacitors faster than the music is emptying it. It will never happen in a transient in a normal amplifier. You have rail sag. You can just put your signal on your power cord. Put your signal generator or the signal analyzer on your power cord and see the music signal is there. It's the same on the speaker wire. It's everywhere, so it bleeds right through the music. It's everywhere. So if you have a cord transformer there, you can only have the music signal below 50 hertz essentially on there, and that's
there's something I hear.
You need something.
Kind of a slowness.
You lose a lot. You lose a lot. It's just not as good. It's not as present. It's not as focused. It's not as detailed. It's not as open. It's not as transparent. It's the same if you make Class A amplifiers, you need to stay in Class A. You cannot have something. This notion of a Class AB amplifier is stupid. Either it's Class A or it's Class B. It's not something in between that. So this is a false. It's a false advertising. Oh, it's a Class AB amplifier. No shit, it's not. It's a Class B amplifier where you use it because nobody uses those 6 watts or 7 watts or 20 watts that you have running Class A in that shit.
What you're saying is an amplifier that's AB, even though it might be running A for the first few watts, it's going to be going into B all the time.
Yeah, it's like pregnant. It's like pregnant. You cannot be a little bit pregnant. You cannot be a little bit Class B. You're Class B when you're Class B. It's like that. And what Class B does is that it asks the feedback network to correct itself. So you have crossover distortions, and you need to correct that in the feedback. But it's an impossible loop. And the spikes, if you look at the spikes in the simulations, the current spikes that you need to put through are tremendously big, and that shocks the amplifier. And that is, again, this narrowing of the soundstage rather than something transparent and at depth. It gets squashed.
So your amplifiers are Class A.
We have this called 880. They run Class A. Even at full, they are not hot. But we have make a bias network that always stays open. So you have minimums 0.63 volts in the bias spread at all time. So we made a very clever bias circuit. And all the heat we put into our amplifiers is through this bias network. We run the drivers that runs the output states at 150 milliamp, where normal amplifiers are running 15, 20 milliamps. So we have 10 times the current. And that means that when the output transistors maybe need 5 milliamps, it doesn't squash the bias spread. And that allows us to run the output transistors at an Oliver bias, which is optimum for the distortions. So we have something that is optimal in 2 places that never goes out of Class A. So you don't get this switching spikes going back in your feedback loop.
But there's still some heat dissipation in the amplifier that you deal with, or is it completely?
Yeah, but not in the output states, just in the driver states. They run. We idle 60 watts approximately. Some Class A amplifiers idle 200 watts or 400 watts or whatever, but we idle around 60 watts. So it gets touchy hot, but not really hot. So, but it's still Class A. Class B is Class D is of course cold, running in 93% efficient. Yeah. So we use those for our lower range products, which are really, really good, by the way. I think Class D will in a generation or two be as good. because every year you get a new chipset. You can switch faster. So that means essentially you can move to less and less and less filtering. I think the main caveat on Class D is that you still need output filtering with a coil. That means you need to add induction to the output. And if you have ever listened to the differences in speaker wires with high induction and low induction, you would know what that does. And that is what Class D does, is that you still need a little inductance there.
Right. So
and
as technology improves, these things can switch at higher frequencies. So the low pass filter becomes simpler.
Smaller, yeah. And less needed. The thing is that what is good for efficiency, when you have an output transistor or output MOSFET in a Class D, you turn it off, and there's a little capacitance in the gate, and that means you need to add a little charge to that before the transistor or the MOSFET turns on. And that dead time, before it can ramp up, that triangle, it says, now you turn on, okay, I will wait a little. That triangle, that ramping up triangle, is a loss. That is a power loss. So naturally, most of the companies doing the chipsets are looking how to decrease the dead time, how to make less and less capacitance on the gates on the output MOSFETs, and they are doing a heck of a job of that. You have
I wonder what the threshold is of where they need to get to for the D to finally.
I think they're already. I think they're already there, basically, because now you can switch maybe 700 kilohertz, and I think that is enough to have a very gentle 100 kilohertz filter. That means that you have absolutely no phase shift, no delay, no drag down at 20 kilohertz where the top of the music is. So I think the chipsets are getting there, and I think the manufacturers are getting, the designs are getting better and better.
Cool. I've also noticed you've taken your obsession with resonance and good versus bad resonance, not just in your speakers, but in your electronics too. You're doing a lot with chassis design, removal of aluminum.
It is a lot of things. It is a lot of things. It's like if you take an output transistor and you mount that on aluminium or you mount it on copper, the output impedance is different. Copper cools better and lowers inductance in the device, so you have a lower output impedance. So you get a better damping factor of using copper rather than aluminium in your heat sinks. So that's one reason. Another reason is that every single component is vibrating, but it's also a microphone. So it's everything picks up noise, vibrational noise. So you want to make sure that what they pick up is at a quality we like. So what we have seen by doing decoupling devices, resonance control devices, these materials that we use there, they are a result of many years of experimenting in that. And what happens when you use this resonance control material in an amplifier cabinet, it's unbelievable. So mechanics of things moves it. It's a mechanics of cables makes a big difference. If your cables are embedded in rubber, if you have rubber in your cables, they sound like rubber. You need hard Teflon. That is the best material. That's the best dielectric. That ensures that you have the least microphonic, and you need something that is very stable in dimension.
And you think a Teflon dielectric is better than an air dielectric?
Yes.
Why?
Because air dielectric does not fixate the center conductor. So it can float around in all directions. So it can vibrate. I know cable manufacturers who have big problems. They're not selling about it, but the main resonance of their wires are 16 kilohertz, and that's a bloody place to have a resonance. So I think that mechanical stability is essential in power cords, power speaker wire, power ports, etc.
So vibration in the power cord has an effect.
Yeah, mechanical stability, vibration Those two go together. And then being a bad antenna and have low inductance and low capacitance. Those are the 5 things you need to look into when designing cable.
So when you've got like 100 miles of copper before your house coming into your house, how does that last couple of meters of a cord negate what came before it on its way into your system?
The noise canceling effect has a big part of that. Yeah. And not being subjected to the mechanical environment of vibration that you create, you essentially create a local feedback within your music system. So the vibration from that, you should not be able to detect. What goes on in the wall, you cannot really control. You can only control what's in your house. And I think that everybody that's been listening to music have had the sense that now it's 4:00 Friday afternoon. All of a sudden, my system starts sounding better. So that's because the quality of the power you get in is getting better. So of course, everything in front of your house also has an effect, but that should not exclude you from optimizing what you have inside your house.
Where does your company go from there? Yeah, where do we go? Where's your head at? What are you trying to do next? Are you putting your energy? Yeah, you like for the company. What's on the horizon?
Right now, I'm pretty stoked about our Streamer DAC concept, and I think that over the next few years, I will try to play that out also into something more affordable. Yeah, I think that is where my head is. Also, all that we learned in the mechanics of our 880 amplifier series is also taking a big part of how to play that out in something more affordable. I want to take more of what we learned of the M speakers and play that out. So there's lots of things to look at, and I think that the thing is, once you have done a project, once you have finished something, then you already know how to do it better.